I asked you to look at the slides, and then you can, there's a lot of reading on this. We're gonna get into the Gaussian distribution and all sorts of notes about this. This is something, let me just explain something about this so you can appreciate it. So, in the real world, when you talk about systems that are naturally occurring, anything like this, almost anything like white noise and amplifiers, the general stuff that happens with an electromagnetic signal associated with radar when it travels and comes back, it's going to have noise on it. All those signals have a statistical variation that's called the Gaussian distribution or the normal distribution. How many have heard of that before? It is ubiquitous. Now, the neat thing about a Gaussian distribution is this, and I put the PowerPoints up. I may reference them later in the lecture. If you have one variable, say y, and it has the Gaussian distribution for it statistically, and you have another variable x, and it has a Gaussian distribution, then the combination of the two added together will have a Gaussian distribution. As a matter of fact, there are, even if you don't have Gaussian distributed variables, if you have, say, x, y, or say a, b, c, d, e, f, g, all these as random variables, if they have the same standard deviation and same mean, the sum of them, a large number, will have a Gaussian. And we'll talk about this. It's a profile that, and there's things called, there's statistical physics and mathematical proofs that show this. I'm not going to do those, but I'm going to tell you the reason we're talking so much about this and we'll be talking about the Rayleigh distribution and the Maxwell-Boltzmann is they are applicable to almost everything that we think of in terms of noise. And in amplifiers and things like this, noise is a big issue, and with radar, the real problem is this, because I'm speaking from experience. You transmit a signal, it comes back. Now, when it goes out, the power density falls off as 1 over r squared. Does everybody follow me on that? When it hits a target and reflects back, the small amount that's reflected, that energy or power density falls off as 1 over r squared. That's 1 over r to the 4th decrease. It's extreme, all right? It's a huge amount. That small amount of noise that will be present on the received signal can be significant in terms of it can cause, basically it can overwhelm the signal. Do y'all follow me on that? So understanding that becomes critical, and I'm gonna try to do a good job on this. I wanted to give you a little reason behind what we do. This is useful everywhere, and a lot of times when you're dealing with any type of high-speed digital communications, errors will creep in, and this will predict the errors pretty exactly. So first, with the Gaussian distributional, does anybody have any other questions? How many took a look at those notes? Anybody? You look at the problems? I don't expect you to understand all the problems, but they're very straightforward. Once you understand the distribution, we'll be talking. Do you all have your books here, by the way? Bring your books to class from here on, because we're going to be referencing tables, and you need to know how to reference these tables. I will provide these tables for you. In the book, he says you can use MATLAB. I use MathCAD, I use other things, but I just want to show you this. And by the way, your calculators probably have a lot of these functions, like the Q normal and all this stuff, and we'll talk about this. So when we talk about the Gaussian distribution, or the Gaussian probability density function right now, I want to start here. In his book, he'll do the distribution first. What this is this? F of x. X is going to be a random variable. We don't know what it is, what it pertains to. It could be voltage, it could be anything. And if it's Gaussian, it has a Gaussian distribution. It'll be 1 over the square root of 2 pi sigma, where sigma is going to be the standard deviation. This is in your textbook, the PDF, and it's also in the book I put up, the older book. Y'all follow me, Cooper and Mill? So this is, you can look online, it's there. Then it's going to be times an exponential. This is a one-dimensional Gaussian distribution. And it's going to be the actual random variable minus the mean value of the random variable. And this, right here, is squared. And then it's over 2 times the actual, and I better put x here. And that is going to be the variance. Y'all follow me?
Is the sigma?
This is minus right here, pardon me. Yeah. What?
Is the sigma part of the square root in 2 pi
Yeah.
sigma?
Mm-hmm.
Okay.
And let me tell you where this is. And I don't have that book.
In the slide, it just had it separately from it. I just want to make sure it's the,
In the one you posted in OneNote, it's on page 67. I think that's the old book.
Yeah, I'm gonna just take a look there for 1 second.
it's on page 172.
I'm sorry. That would be sigma squared underneath it. I'm very sorry. This should be like this. You can put sigma squared there, but I'm sorry. That's right. Sigma of x, my bad. My bad on this one. So this is the probability density function, and here x bar is the mean. The mean value a lot of times is given as mu in our book. Sigma x squared is the variance of x, or just VAR of x in our new book. And then sigma x is going to be the standard deviation. Okay. So that's basically it. Now I'm going to tell you that this functional form is the probability density function. Here's the way it looks. If the mean here is going to exist here, and this is the probability density function, f of x, then the peak value is going to be here. It's going to look something like this. Got to make note of a few things. If you look, what is the peak value going to be right here, just by looking at this expression? Well, this is the variable x is shown here, and this is the mean value. So at the actual value of x prime, this is 0. Do y'all follow me on that? Right? X minus x prime would be, or x minus x bar would be 0, right? This is the mean. And that means you have e to the 0, which is 1. So this is the peak value right here. Just point. So it's 1 over square root of 2 pi sigma x. That's always going to be the peak value. Now that's a probability density function. So anytime I want the value, the probability, first there's a couple things to note about here. First is obvious, the integral from minus infinity to infinity of f of x dx is going to be 1. That's got to be the case. All right, it has to occur. If we're talking about an event, then the probability of occurring over all possible values has got to be 1. That's the only thing it says. The next is, they usually talk about the characteristic function or the probability distribution, and that's equal to the integral from minus infinity to x of just f of x dx, or it's equal to the integral from minus infinity to infinity of 1 over the square root of 2 pi sigma x, and then it's going to be exp. Actually, this is x here, my bad. And in the book, he's going to do it this way. He's going to put u minus x bar squared over 2 sigma squared and du, because it's going to, the end point of the integration is going to be x. And this is the probability of, really, it's equal to the probability of the random variable x being less than or equal to small x, which is going to be a value that you choose. Y'all follow me?
It's not negative.
Huh? Oh, yeah. Gotta have a negative. I'm sorry about that. Y'all follow me, class? Wow, something else about this. A lot of times, they're going to take this function and they're going to normalize it. It's called a characteristic function. I'm going to show you this. And from here on, you're going to need to be attentive. This gets a little bit tricky. How many looked at these notes and stuff? Okay, if you looked at them, you realize that we're really going to be referencing tables a lot. But your calculators will do this too. Nowadays, your calculators, if you get them out and learn to use them, you won't need tables. They'll do everything, pretty much. So now we talk about something called a characteristic function. And the symbol he uses is this. And this is normalized, so this is normalized. And what by that it means is that this is equal to the integral from minus infinity to, and this is going to be small x, and it's going to be 1 over the square root of 2 pi But here, it's assuming sigma is actually 1, and it's going to be times exp to the minus quantity x it's really going to be, sorry. Where's my eraser? I almost feel I should use a different variable, but I'm not going to. If you look in his book, he's going to have this. It's going to be minus x squared over 2, and it's I can't use x here. I need another variable. I'll use u squared du. And I'm not sure what page it's on, but it's in the notes. You got a page number on that?
The slides.
It's on the slides. What slide?
It's on slide 50.
All right, slide 50. That's the characteristic function. And here's the neat thing. If you wanted to use this, which have the tables in the back of the book, y'all follow me on this, class? These are tabulated for all sorts of values. You can get this by saying that f of, now I'm going to use their value right here of x, is really going to be the characteristic function. And here, it's going to be this value of x minus the mean value of x over the standard deviation. And I don't know where that is. It's stated in the book, it's stated in both of our books, and it's on the slides. That's the characteristic function. Y'all with me? So it means if you want this, a cumulative probability, you can use this. With me? So now what we're talking about, probably the best thing to do is probably go ahead and do some problems. And that's what I'm planning on doing. Actually, I'll talk a bit more about the Q function. I'm going to put them all down, then we're going to apply them to a lot of problems. That's where you'll see all this. And then I hope you have your text. So this is the characteristic function here that we use, and it's tabulated in the back of the book. There's one other function, it's called the Q function. I'm going to put it up here. And we use this all the time. Or at least you should be familiar with it. Nowadays, you can, the calculators and stuff and the computers, I mean, just standard MathCAD or MATLAB, they have all this in a closed form, functional form, just like sines and cosines. So next, if you look at something they call the Q function, the Q function, Q of x, this is again a normalized function. It's equal to the integral, here it is from x to infinity. This is not, I didn't see this in the book, by the way, as far as this discussion about to have with you. And then it's going to be 1 over, and it's normalized, so I'm going to put down, this is normalized as well. Square root of 2 pi, and then it's going to be exp. Here, it's just going to be minus u squared over 2 du. Now, those two functions, if you look, this is q, by the way. Maybe I better make sure you can see it's q. It's not supposed to be the characteristic. That's the characteristic function. This is the q function. If you look at q of x plus the characteristic function, better do it carefully, plus the characteristic function of x, it's always 1. You all follow me on that? Just take a look at this. You integrate, this goes from minus infinity to x, that goes from x to infinity. It's a probability density function. It has to be equal to 1. Do you all follow me? Now, some other things to note. If you talk about this function, he's going to do it this way. He's going to have the characteristic function of minus x is equal to 1 minus the characteristic function. And I'm not sure what page this is on. He actually does q of minus, q of minus x is 1 minus the characteristic function q of x. Now here's why. Listen up. For both the characteristic function and the q function that is tabulated in the back of the book, they don't have negative values of the argument here. So if you have, after you normalize, a value that's like q of the characteristic function of minus 2, then what you have to do is say it's 1 minus the actual characteristic function of 2. With me? And here's what we're really doing. If we look at these normalized functions, remember what they're trying to do is provide you information so this integration here can be tabulated for any possible values of mean, standard deviation, and value of x. Do you all follow me? That's what they're trying to provide you. This is a cumulative distribution function. So if you look, and I'm just going to pick a value, suppose we look at actually the statistical distribution of just inside this thing. This is the kernel of integration, and just call that, I guess, f of u. And that's equal to 1 over square root of 2 pi exp to the minus u squared over 2. And you plotted it. It would have a peak value at 0. And it would look like this. Now, if you pick any value here, just call it A. If you wanted the probability of the event occurring, for all values from minus infinity to A, it's this area, right? This area right here is just going to be the characteristic function evaluated at A. If you wanted the value, or if you wanted the probability of the event that it was greater than, let me write that down here. Suppose you want the probability of, and I call this u, of the random variable u being greater than or equal to A. That's simply equal to characteristic function of A. And the probability of, sorry, I did that wrong. It should be of u being less than or equal to A. And the probability of u being greater than or equal to A is simply going to be the Q function of A. Can you all follow me? This is the blue area. Agreed, everyone? I don't know.
Would it not be 1 minus?
Yes,
You
it
did
is.
1 minus the.
It is. That's exactly what this is.
Oh, because, okay,
Yeah.
I got it, I got you.
If you look here, these two added together are 1, right? So 1 minus the characteristic is the Q. That's all it is. All right. Now, he has a few other functions that he mentions in the book. The error function, and he mentions, I want to do the approximation. I'll put this up here. I'll put the error function there. That way we'll have everything out on the board, or it will be at least something we've discussed, and then we're going to apply it to problems. You're going to use the error and complementary error function a lot when you get into microelectronic processing. Have you done all sorts of stuff with microelectronic fabrication yet or not? I don't think you get, I think it's a senior course. You're going to be using error function and complementary error function to find out how the density profiles for all the dopants you put into a semiconductor, how the density profile actually comes about and what it'll look like. So, it gets interesting. Anyway, over here, I'm going to put down the error function. We'll talk about this when we need to, but it's useful to also know the error function itself, and I'm just taking this from the way he puts it in his book. It's ERF of x. I used to use this a whole lot, and it's simply 2 over the square root of pi, and then it's the integral from 0 to x of exp to the minus u squared du. Very, very similar to a lot of the functional forms, except we take the 2 and the pi out in front here. This has what? 1 over the square root of 2 pi, right? For the normalized. Here you got 2, but you'll notice the integral starts from 0 to x over pi. And then you can find that the q of x, and this is in the book, q of x itself is equal to 1/2 times 1 minus the error function of, and it's x over the square root of 2. Here's one of the reasons I'm going to tell you I'm putting this information down. Your calculators, the old days, the calculators always had an error function, but they didn't always have a q function or a q normal function. Follow me? So this is useful for that reason. And finally, if you, I gotta tell you this, when you look at like, I don't have it here, but if you look at the value for Q of X, just follow me on this, guys. Suppose you have Q of X, or Q of U, we'll use X. Q of X is equal to the integral from X to infinity of 1 over square root of 2 pi exp to the minus u squared over 2 du. Now, what we're really looking at, say this is 0 and this is going to be u. It looks like this as far as the profile of the density function f of x. But if we wanted the value of, say, x here, where x is going to be greater than 3 or something like that, you can see one thing. The area here is going to get very, very small. Y'all with me on this? And what they do is, and they say if it gets really small, we can actually cap the value of this integral, and he has this. It's an approximation, so please write this down. Approximation of Q of, this is Q of X for X greater than 3, approximate. So you're going to get Q of A, and he'll use the term A instead of X, so it's the argument of the Q function, is approximately equal to 1 minus 1 over 2A squared. Then it's going to have 1 over A, and then it's, the way he does it, he's going to have the square root over here. 1 over square root of 2 pi here, and then it's going to be the exp of minus a squared over 2. And he has this in the book, but this is an approximation. Now, why do they use this? Because when you get above a certain value, this approximation will give you a very highly accurate answer without actually evaluating the integral numerically or looking up tables. That's it. It's the only reason. By the way, the tables don't go to any values greater than or less than 3, or greater than 3 if you look. I don't believe, if you look in the back of the book at the Q tables or at the characteristic function tables, and you won't find them for anything greater. Well, I take it back. They have it for values all the way up to 7 in this book, but you'll find out for after 3, this will get you everything you need pretty much. Yes, sir.
Sorry, what did you write after 1 over square root of 2 pi? Is that equal sign?
It's just-
Same with the board.
It's multiplied.
This is times this, right?
To the right of that.
At the same.
Minus.
You went to the other side of the board. He's saying what's in
What's
between.
here? exp, exponential to the minus a squared over 2. It's just this. It's basically taking this value right here, putting it here, and then weighing it by this.
Okay.
That's it.
You're multiplying it by the.
Yeah. It's in your book too. Now for some problems and stuff. I think that's all I need to do. Oh yeah. So he gives a thing with IC triggering, and I'm trying to go through these systematically, and it'll answer your questions, believe me, I hope. Oftentimes professors just use PowerPoints. They'll say, here's the formulas, and they'll start applying them. But a lot of times it doesn't quite sink in. So I'm going to go ahead and do it this way. I put up all those values. I'll put up the functional forms. If you haven't read the book, this is going to be something you need to pay attention to, because some of this gets a little confusing. Remember, these are probability density functions, and this is statistical information that has to do with the likelihood of occurrence of events. Okay, so in the example, he says this. This is in the reading. He's got an IC device, an integrated circuit, and it triggers if a voltage is greater. This is a trigger point. It triggers if a voltage is greater than 2.5 volts. And he says for this device, there's an actual average value of the signal on the line of 1.5 volt. So just think about this. This is the sort of a DC value of voltage. that's at the present. But there's gonna be noise superimposed on this. So when we talk about the noise signal that is Gaussian, it's assuming the profile is Gaussian, he gives you a value of sigma squared being 0.2, and the units of this will be volts squared. Remember, the standard deviation would be in volts, but the units of this are V squared. And he gives you a mean value of, I got the mean, I got that. And so he wants, with this particular profile, and now listen, this is where, y'all follow me? I'm giving you the mean value. 1.5, or I mean the average value, 1/2 volt, that's what's on the line. Think of it as a 0. And there's a threshold of 2.5 volts where it would indicate something false. Basically, it would indicate a 1. Y'all with me on this, guys? That's the reason we selected 2.5 volts. That's the point over which the thing would trigger. The circuit would actually do a transition. So what's the likelihood of this occurring? Y'all follow me? If it's Gaussian distribution. Now I'm going to write down the formal integration. So the actual probability of this event occurring of V greater than 2.5 technically is equal to the integral from minus infinity, I'm sorry, it's the integral from 2.5 out to infinity of 1 over the square root of 2 pi. And then I have to put the standard deviation here, which is the square root of that. I'm going to just leave it as, for now, a square root of 0.2 right here. Y'all read, you follow me the reason why? Because that's the standard deviation. And then it's going to be times exp to the minus, and here you have the value that we're going to integrate over of u, I'll use x here, of x minus the mean value, which is 1/2, or 0.5 squared over 2 sigma squared, over 2 times 0.2, and it would be dx. Now, if you can evaluate this integral, it'll give you a right value. Y'all with me? Now, if you want to use the Q function, you look, you're going from 2.5 to infinity. The range is from some point to infinity. You all with me? So if you take the Q function, what this is going to be is actually the Q function using the value of 2.5. That's the trigger point, or the bottom integral, or you would call it x in terms of a general argument, minus the mean, which is 0.5, over sigma squared, which is, over sigma, not sigma squared. The Q function uses sigma down here, so this is going to be the square root of 0.2. What that is really, here we're going to look in the tables. That's, I think this is 4.473. I did all this last night. Hold on. I think I've got it on MathCAD. And,
What page does that take on?
hold on for 1 second. Let me do this. In the old book?
In this book. Cool.
Oh, that book? Oh, gosh. I don't have it with me.
Yeah, I've been trying to flip through and find it.
Just look up Q. Huh?
This problem, page 82.
Of the old book. Here.
I don't know about the tables.
I can give you this. Let me see. I think he's got the characteristic function on page 567. And this book may only show you the characteristic function. You can just use 1 minus this will give you the Q function.
Okay.
We'll do it. So if you take a look at this, now I gotta open my tab. I'm gonna show you all this. I better pop this open right now and get it going. It's a 4.472. This should be 4.472. Y'all follow me on this, class? That's the argument inside the Q function. That the tables are on in the old book that I put up there on page what?
I didn't find it.
Oh,
There's
no.
problems on page 71.
All right, so I want you to look at the tables. Now, this is also equal to 1 minus the characteristic function. And those tables are, I showed you that, he calls it, this, what I'm calling the characteristic function of x is really the cumulative density, I think it's CDF in his book, isn't it?
It's CDF. It's on page 567.
All right, that's the second. So here it's going to be, I'll just use characteristic function of 4.472. Now, this, if you evaluate it, if you go to the Q function I evaluate, I'll show you this stuff. If you do it, what I get for that is about 3.872. I think he has 3.875 in his book, and it's times 10 to the minus 6. I evaluated this numerically. If you look at his table, you have to interpolate. All right. So if you look, why don't you look in your book at the cumulative distribution function? Which page is that on, by the way?
It's on 567.
It goes up to 3.4.
Huh?
It's from negative 3.4 to 3.4.
That's it? It stops at 3.4?
This is standard normal CDF.
Okay, our book goes a little further. I mean, the old book goes a little further in the tables. If you look at ours, tell you what, we'll do it this way. Why don't you do this? Just take a look at the Q function here. All right. Tell me what you're gonna have to interpolate. So he's gonna have numbers in this column. We'll talk about this. He's gonna have numbers here that are like 3, or he'll have 4.1, I think is it 4? 4.1 is the next, 4.2, da-da-da-da-da, 4 point, and this is gonna be 4.4, I think is that right? And then over here on the top, he's gonna have values of like 0.01, 0.02, 0.03, and so forth, 0.04, and 0.05. What page is that? Is it page 567?
No, this is page 435 in the old book.
Okay, so I wanna make sure I put this down. Page 435,
435, yes.
and this is old book. I'll get out of your way. 1 second. All right, and this is the Q function, by the way. So if you look down to, remember ours is 4.472, so here's 4.4, and now I gotta look at out here to 0.06, 0.07, and 0.08 here. Now you're gonna see something right here. If we look over this column, remember this is the Q function's value. And if you can look at your calculators, especially those with newer ones like the Inspire stuff, you probably need to look online for this. I believe they have this function in there, and I don't know what the name of it. I didn't look this up for TI stuff, but modern calculators have all that. Does yours have this in it?
Yes.
You have an HP though.
Yeah.
All right, that doesn't count for these guys. Most of them have Inspire, I think, don't they? HP, I like that too. It's got a lot more focus on. All right, so we have 4.472. Here's 4.4. Come over here. Here's 0.7. I think it's 0.7 and 0.8 is the next one, isn't it? Take a
It
look.
goes in 0.07, 0.08.
All right, so what's this value here? 4.47 is what?
So it just goes from 4.4,
The value though.
and then that is at 0.08, or no, 0.07. That is,
I'm just showing you what you have to do.
0.39.
Say that again?
Yeah, 0.39 times 10 to the negative fifth.
Times 10 to the minus fifth? Is
Yes.
that right? Okay, and what's the next one? 0.
For 0.08, it's 0.373 times 10 to the negative fifth.
373 times 10 to the minus fifth. All right, now this is 7.2, so if you want to draw this, you'd assume you do a linear interpolation of this. But if you come over here and you look at the difference in these two, you take 0.39 times 10 to the minus fifth, and then you're going to say this is going to be 0.375 times 10 to the minus fifth. That's the delta difference. Do y'all follow me in this class? With me? So if you take that and you divide it by the distance here, which is 0.01, now you got the change of Q with respect to, I'll call it just X here. You're gonna get these two things. So this is 10 to the minus 2, and this is gonna mean this goes to 10 to the minus 3 on top. But then what you do is take this value, and then we're gonna interpolate, or excuse me, take this value, and from here to here, I'm actually gonna go, so this is only 2 over this 8, so it's gonna be, you can do it this way. Whatever this is, actually, you don't need this right here. You can just say that if I want the actual value, the Q function, Q of 4.472, I'm gonna take the lower value here, which is 0.375 times 10 to the minus fifth. Now I look at the difference from here to here, whatever that is. So I can take the 10 to the minus fifth out in front, and then you have 0.39 minus 0.375. Take a look at that. That's gonna be the spread, but I only go 80% of that, so I multiply this. Boy, this is kind of messy, but take this whole thing and just multiply this by 0.8, because it's only from here to here. We want to go to 0.072. Well, if you go from 0.070 to 0.08, there's 10 deviations. So, but we want to go from here, this is the smaller one, to here, so we can subtract off lesser, so it's 80% this way. And that yeah, that should be the value. Oh boy, wait a second. My bad, I did something wrong here. I've got myself in a corner, hold on. You all know how to do interpolation, right? All right, so this is a linear interpolation. The only thing you need to do for this, the value, I'll just call it Q at I should put the whole thing, 4.470. That value is going to be subtracted from Q of 4.480. Now that's a difference, call that delta Q. And I'm not going to put the numbers down, but you all follow me what I'm doing? That's the two values there. Now to get the actual value of Q of 4.472, I take the lower value, I'm going this way, Q of 4.48, and I'm going to add to it this difference, delta Q, and I want 80% of it, because instead of going the full 10 over, I'm only going 8 over from that point. So this is going to be times 0.8. And that should give you the number real close. Can you do that for me, please? This right here is the thing. That's 0.375 times 10 minus fifth, or plus 0.8. What's the difference in these two? 0.0015, isn't that right? That should give it to you. Can you tell me what that is? I think that's right. Oh, I think that's 0.015. My bad. Anybody?
I go like 3.87 times 10 to the negative 6.
Now, here's an answer.
3.875 times 10
Yeah, and I got 3.872 times 10 to the minus 6. Now, his is based on a MATLAB exact calculation. Right? But that's how you do it. And just for the record, all right, I'm not gonna kill you if you're, off in the third decimal point. All right, you all follow me on this class? You've got to be accurate, but I don't expect absolute precision, especially if you're interpolating, and I'd understand that. Now, your calculators, you've got a calculator that does it. Who has an Inspire that figured out how to do it? I'm pretty sure they do it, but I can't say absolutely sure that they do it. Most modern calculators bought within or engineering calculators will have this available to you. but I don't know how they label that function or how it's accessible. What is yours? Is yours a TI?
Inspired Phoenix.
Did you find it or not? It's in there. Just look under statistics or probability, and you want, yeah.
I know how to find it on the 89.
What's that?
I found out how to find it on the TI 89.
Does anybody have a TI-89 here besides you? What did you use? Do you know how to find it, sir, or not? You found it? Okay, never mind. If anybody needs to know if you got an 89, just ask them. Okay, I wanted to mention that. This is the Q function and the characteristic function. If you take 1 minus the characteristic function, you'll get that value. Or just get the Q function. Now, you can evaluate it. In modern computers, you can probably, or modern calculators, they probably have this as an actual function. So I wanted to do, anyway, when you do that, that's the probability of it actually triggering. And then he has a second part to this. He asks, I forgot exactly what he asked, but I want to get through this part too. He asks, tell you what, why don't we jump to the problems now? You can read that in the example. All right, now that's the probability of it triggering, right? What's the probability it doesn't trigger? 1 minus that, right? Now, if you want the probability, the cumulative probability that it triggers in n attempts, you would take 1 minus, and the probability it doesn't trigger to the nth power. Do you all follow me in that? This is discussed in the old book on page 1. Well, if you don't have it. But I want to make sure that you take a look at this. We'll do a lot more problems with this. I think I can do this. I think I can put the power, I think I can use the overhead and show you what I'm doing on MathCAD, and then we can go through the problems kind of quickly. But I'm trying to make sure that you understand how to do these things. Now, I did it on MathCAD because it's easier for me to whip through these problems. Let me go ahead and try to get this on the overhead. I've thought about the best way to teach this. Honestly, those tables are probably antiquated. Most of you probably have modern calculators and stuff that will allow you to forego that and just use your calculator. And I mean, we've got it on an HP, you've got it on a, what's the other one? The TI-89. I'm sure the new ones, the Inspire, that's a newer calculator that does it too, but I don't know how.
Is it related to the CDF?
Yeah, the cumulative distribution function is really the integration from minus infinity to that point. It should be cumulative distribution function normalized, right? Or does he have something?
Normal CDF.
If you can put in the actual value of the mean and the variance or standard deviation, that's how a lot of these have it.
I think that's how this says it.
Yeah, that gives them, you could put a mean in of anything, right?
Right.
Look, that's it. So you can do the entire thing without, you could, here, just do this. Tell you what, you don't even have to do this. See this? We got a lot of stuff up here. Hold on for 1 second. Here's what I want you to do. That's normal distribution, right?
Yes.
All right, so do this. We know that what yours is calculating is P of X being greater than some value A, or some X. I'll call it X. All right. X being greater than, sorry, no, yours is less than, yours is cumulative, so like that. So what is that? That's the integral from minus infinity to the value X in the function of 1 over the square root of 2 pi sigma exp. This is what yours is doing. Minus, that's going to be X minus the mean. You'll have U there over sigma, 2 sigma squared du. Yours is calculating that. Okay. So for ours, we had a mean value or a U value of 2.5 in that problem. Just try this. I want to see if it works. And this is an Inspire, right?
Right.
How many have Inspires here? Okay, so you guys listen to this because he's found it.
It's normal CDF under the probability.
And the sigma of ours is the square root of 0.2. I don't know what that is, but it's 0.47 something, I think, times 10 to the minus 1. Isn't it? What is it?
Yeah, you can put square root of 0.02 or 0.2 in there.
0.2. All right, then you can go for your function. It's what's the symbol for? Normal CDF. Okay, that's fine.
Do you
So-
put 2.5 for the mean, or do you put 0.5?
Well, we're gonna take 1 minus this. Oh, no, the mean itself is 2.5, or, sorry, 0.5. Trying to run through this too fast. You with me? That's the mean. So with this, remember, this is from minus infinity to x, right? What we want is actually 1 minus this, right? So we want 1 minus n, this is the normal cumulative distribution function. And the value will go here, so it's from 2.5, right? And then I think the mean is next, right? That's 0.5, and then the standard deviation, which is square root of 0.2. And this will be the probability of random variable in x greater than 0, or greater than 2.5, right?
Yes.
Tell me what you get.
So what are the bounds?
Well, you're gonna take, first in the normalized cumulative distribution function, you're gonna enter 2.5 for the value, for x, the first value, all right? Then the mean is 0.5. And then the standard deviation is square root of 0.2.
What's the upper bound?
The upper bound's
Infinity. Infinity, but you're gonna take, here, we're going from minus infinity to x.
3.8 times 10 to the negative 6.
Yep.
When I did that, I got 3.8 times 10 to the negative 6.
And what was the answer?
Like 3.78 something.
All right, and I bet you get a rounding. Do you have something where you can tell it how many, if you want double precision? Pardon?
Excuse me?
Can you tell it what level of precision you want?
Oh, I got 3.875. Yeah.
That's right.
That's what I got.
And
So,
that's-
and I got 3.88, but, yeah, so
Round.
for my lower bound, yeah, I couldn't do negative infinity, so I just did like -9 times 10.
Normally, it has something that starts in minus infinity for the cumulative distribution function. Y'all with me? Let me just show you on mine what I did. Just bear with me. Don't worry about the lights, because I'm gonna be going back and forth to the board. So, here's what I did.
Oh, you can't do it, you
Let-
can't do it on this one.
Hang on, guys. Here's what I defined the normalized distribution function in MathCAD. All right, I wanted to make sure it's the absolute definition with me. And this thing will iterate until it gets an accurate assessment of that. Then I can set the level of accuracy, I believe. So for our problem here in 2.51, I hope you can, let me go a little higher. And I called it QQ because I use Q of A to be the approximation I was checking. So for ours, it's for x being greater than 0. Oh, sorry, my bad. This is the example in the book, sorry. This is the example in the book we did. But I did that example and it's easy to do. I'm gonna do the examples in the book now. Do you all follow me what I'm doing here? How we did it? How many can understand that? I'm sorry, I'm being a little, do you follow me? Your calculators have this. This is the thing I'm really trying to underscore. You have the ability to forego the tables, which is, in my opinion, priceless, because I hate tables, especially steam tables when I took thermal. I hate it. Now, let's do the problems in the book. I got some time yet. So the first one I want to do is 2.51, but we're gonna whip through this. If we have, you know, I can literally put up, like he can put up things where you enter the actual variance and the mean and just the value you wanted evaluated at, like, and it will do it for you. And but the normalization process was very useful if you had tables. You didn't have to do it if you've got that function, because yours doesn't. All right, so 2.51, just tell me what it is. 2-5.1. Please be attentive here. If you didn't do them, be really on topic here. You're getting a quiz on this on next class, so just pay attention. 2-5.1. There, I gave you that set in the 2.7 business, but I don't have time for that today. Go ahead.
Gaussian random voltage has a mean value of 5 and a variance of 16.
All right, mean value of 5 and a variance
Of 16.
of 16. Go ahead.
What is the probability that an observed value of the voltage is greater than 0?
All right, now, everybody follow. We could draw the density function, but it would look something like this. If this is V, then the mean value is 5, that's the peak value, and it would look like this. And this would be the probability density function, F of V. Y'all follow me, class? Just to get a visual. Now, what he's asking for is the probability is V is greater than this, right? That's this here, isn't it? It's that area, right? You all see how a normalized Q distribution would give us that? Q always has the area above a certain threshold, but you have to account for the normalization. You all with me? We can use the tables or we can use the actual, I do it both ways. I did all these things last night and I made sure the tables agreed with what I got. And there are a few wrong answers in the book, by the way. I'm just gonna tell you where he just multiplied stuff out or the guy was using the wrong information to do it. So if we look at this, what is this gonna be? Well, technically, if we say greater than 0, right? Isn't that greater than means Q, right? So this is gonna be the same thing as the Q function evaluated. Now, you put in the Q function, it's always gonna be, he'll have this form, x minus x bar over sigma. So for our case, it's the Q function, and I gave you my book, you can look at the tables. Q of x, it's greater than 0, so it's 0 minus the mean value of 5, and that means this is 4, isn't it? If sigma squared is 16, sigma v is 4, square root of that. You all with me? Okay. Now, what's the problem with this? This is Q of minus 1.25. So if I use the tables in the book, I can't, there's no negative values in the old book. Do you all see that? All right. I mean, this is the old book tables. I will provide you those tables of the old book, all right? Because this is the ones I'm referencing in class. In the new book, he doesn't have the Q function. I prefer the Q and the characteristic at the same time. So what do? I say that Q of minus 1.25 is really what? 1 minus Q of 1.25. In other words, you all follow me, the reasoning behind it, class? And what's this gonna be? This is gonna be Q of minus 1.25 is 1 minus, and you can look it up in the tables. You can look this one up in the Q function. I don't know what the value is, but you can look it up. And you can see right here, I've got that. Can you all see that? I got 0.894, but and I checked the tables. I think that we're gonna get, they're literally overlaid. Did you get that? And did you look at the tables or did you look at?
The tables, the old book.
What is in the old book? Can you see it? Now your function will do this. How would you do this with a cumulative distribution function?
What's the upper bound?
Infinity, remember?
What's the lower bound? 0.
What? Oh, yeah, that's, so, can you see this, Chase?
Yes, sir.
Okay, you understand what I'm talking about here? Take a look, all right? And remember, the key is, we want this area, right? This is the statistics for that area. Technically, we could write the integral formally and evaluate it, right? This is the way to do it, the Q function. And did you get that value? You should.
Yep,
What did you get? 0.894?
that's right.
All right. Now you can use a cumulative distribution function, cumulative distribution function on your
Normal.
calculator using that. You know how to do it on your HP. You know how to do it in your TI. Yeah.
Why do we want that area not
Well, what does it say? It wants the probability of it being
bigger than 0 or?
greater than 0. Actually, I'm showing you, it should be this area. My bad. Right there. I'm sorry about that. And so it's greater than half. By the way, question for everybody, and be attentive. So what's the probability of it being greater than 5 volts? 0.5, less than 5 volts?
0.55.
Right, that's exactly it. Whenever you find the mean on a Gaussian distribution, half of the area is above it, half the area below it. Just remember that. It applies to a lot of things. Okay? Is there another part of that problem, 2.51?
What is the probability that an observed value of the voltage is greater than 0, but less than or equal to the mean value?
Hold on. All right, class, I want to make sure everybody hears this. So it's this is part 2, right? Part B. So it's 2-51 part B, and it's what's the probability of the voltage being what?
That an observed value of the voltage is greater than 0, but less than or equal to the mean value.
To 5, right? All right. Now, we can do it with characteristic or we can do it with Q. What I'm really saying is, I can say the probability of 0 greater than V less than 5 is really the probability of V being greater than 0 minus the probability of V being greater than 5. Do you all agree with that? This is one way. You all follow me? You know, in your calculator, or probably you can literally put the lower and upper limits on. I think you can on yours. Now, problem solved. You don't even need to do what I'm about to do. So when I look at this, if I'm using, just take a look at this. What is the mean?
5.
5. What is this?
1.5.
0.5. So I can say this is P of V greater than 0 minus 1/2. What was the first part? P of V greater than 0, right? Y'all follow me? So this is given to us 0.894 minus 0.5. It's 0.3 something? 3 what?
394.
394. I think it's up there too, right? Right there. Y'all with me? Then he says, what's the third part? And I did these all. I looked at tables and I did them with, I'm using MathCAD here. You can use MATLAB, but your calculators are perfect for this. What's the next one?
Greater than 10.
All right, so what is P of V greater than 10? Now I'm going to give you a hint. You can use Q. Remember I said that approximation? What we're really looking for is what? The Q function. And here we take the value of voltage, it's 10, right? That's the value. We're going to normalize, so we take the value there, minus the mean value, 5, over sigma. And sigma was what?
6 to 4.
Pardon me? 4, right? So what is this? This is Q. Actually, you can't use the approximation, my bad. Q of, and this is going to be of 2.5, or 1.5, right? Wait, that. Q of, 1.25. Now, we got that already, didn't we? We got that in the earlier part, didn't we, class? So what's this value going to be?
0.894.
Pardon me?
0.894.
1 minus that, right?
1 and 5 or 0.105.
Yeah, that sounds right. Is that what's up there?
Yeah, it's it runs up to 1.
Yeah, I'm sorry, the mark.
What is your double Q notation?
Pardon me?
Why is there 2 Q's?
I use Q, here, I'll show you why. I'm using Q2 to be the Q function in our book, the actual Q function that's tabulated. I had Q up here. If you look at that, remember that approximation I gave you right here? So what I'm doing is for large values of that argument X, when it's large, over 3, I compared them and they're almost on top of each other. So that's the reason I put that there. I'm using Q here, sorry. Yeah.
For the Inspire, you're able to set your top bound to infinity so you can use it as a Q function.
It's what?
You can set your top bound to infinity and your bottom.
INFTY or something?
Or, no, for the,
Is it got a symbol or does it got you gotta type in INFTY?
it has a symbol for it.
Okay, that's all. Y'all hear that, class? And please, if you have questions, do we have a group me or a Facebook kind of thing for this class?
Yeah.
All right, post them and please access that because it's quizzes coming up. Chat among yourself. It'll help you. I promise you it does. Especially if you don't understand something. It's usually something, but there's a subtle thing you don't understand that's trivial. That's it for 5-1, right?
Yes.
All right, let's go to the next one, 5-2. Do these as quick as possible without going too fast. And forgive me for being a bit clumsy on some of this stuff. Go ahead.
It wants you to use the stuff from the previous
Go
problem.
ahead, go ahead. What does it say though?
Find the fourth central moment.
Okay, all right, this is good. So now we want the fourth central moment. I didn't have time to talk about this. But anytime you have a Gaussian distribution, and this is on the PowerPoint, I might as well show you on the PowerPoint. When you have a Gaussian distribution, which is nice, life is good, usually. So,
So we will be quizzed on this next class.
yeah, let me just finish this before we get, look, right here. This is in the slides. See, when n is odd, if you have a Gaussian random variable, all the odd central moments, these are central moments, y'all follow me? It's x minus the mean, and that bar means the value of that, the expected value. And the n is just the value of the moment. So all the odd central moments are 0. Hear me on that? If it's a Gaussian random variable. The even central moments, and this would be for this, the even central moments are 1 times 3 times 5 times whatever the value of n is minus 1. You keep on doing that. And then times sigma to the end. You all follow me? So let's do this problem in light of that. So for this problem, what does he ask for? This is 2-5.2. Go ahead.
The fourth central moment?
All right, so he's asking for this. He's asking for v minus 2.5, because that's, I'm sorry, 0.5, 0.5. That's the mean value, right? Fourth moment, this bar. You all follow me? All right, if you look there, what is this? This is going to be 1 times 3. Well, can't go higher. And it's going to be times what? Sigma to the 4th power. You all see that? You all with me? Can you see it?
No, where do you get 1 times 3?
1 time, it's supposed to be times.
Okay.
3 times 5. I'm sorry if it doesn't. I don't know why it didn't show, but these are all times each other.
Okay.
1 times 3 times sigma to the 4th, all right? So that's 3, sigma was 16, what, right?
Yeah.
So it's 16 to the 4th power. What's that? This is wrong in his book.
Wait, what's six?
Sigma was 4, the variance was 16.
Yeah, but, oh, squared. My bad, you're right. What is that? 780 something?
3 times 4 squared, 3 times 16.
I forgot. I think it's 780.
768.
What is it?
768.
That's, I think, right. That's wrong in the book. Anybody notice that? If you didn't do the problems, you don't notice it. But that's, I believe it's wrong in the solutions. You can check if you take a look. Isn't it wrong? It is, at least in the solutions manual that I have. And what's the next part? So that's the 4th central
They
moment.
just want the fourth moment.
All right, now the 4th moment is different. When you take a look at that, the 4th moment is this. That's 4th power bar, right? It's the expected value. What this is the expected value of x to the 4th power. Now hear me on this one. This one, if you think about it, is really going to be equal to the integral from minus infinity to infinity of that Gaussian distribution f of, and I'm going to use x here even though it's v, and then it's going to be x minus the mean value to the 4th power dx. Now that is not something simple to do. You have to take this, first square it out, then square it out and multiply those two things together. But at the end of the day, you're going to find out, and he has this in the lectures, or he has it in the book, and it comes down to the lecture slides as well. The expected value of x to the 4th, and I think I put it there, I think it's here actually. Let's see. So here it is here. It's 3 sigma squared, or I'm sorry, 3 sigma to the 4th, right? It's 3, and you can do this, to the 4th, plus 6 times sigma squared, and then it's going to be the actual value of the mean squared, and I'll use u here, plus, and then it's going to be 3 times u to the 4th power, I believe, and I've got that.
And his
I'm sorry.
solution, so he says you
Sorry,
use the 4th.
just mu to the 4th, you're right, you're absolutely right. I did this whole thing, I squared it out on paper and stuff, but I found it, when you look at this, for r's it would be 3 times sigma to the 4th, that's really 3 times 16 to the 16 squared, plus 6 times 16 times 25 plus, and that's going to be 25 squared at the end. And I've got that down here, and it comes out to, and it's wrong in the book, 3793.
Wait, so where do all these numbers come from? Like, what is the 6?
What's that?
What's the 6?
When you go ahead and do this physically and multiply it out, you're going to get the expected value of x to the 4th there. That is the 4th moment. All right, then you take that to the other side, and then the rest of it, like we've got central moment, this is the central moment. Then if we want x to the 4th, actually, this is wrong. I'm going through this too fast. This is actually fourth central moment at the expected value of x minus x bar to the fourth power. But you can see, because I have f of x times x to the fourth is one of them, that will be the fourth moment, and you take it to the other side. We have this information here. We take this and expand it, and it comes down to this. Trust me on it. I'm not going to ask you for a fourth moment or something like this. But you will need to be able to get the central moments and like if I ask odd moments, those are basically, they're gimmies, right? Because odd central moments, not odd moments. All right, that's the, that's what, part 2 or 3? Part 3? What else does he ask for?
Part 3 is the third central moment.
All right, what's the third, listen guys, what's the third central moment based on my discussion? How many know it's 0? It's odd, right? It's 0. What else?
And then he's asking just the third moment.
And how do you get the third moment? Well, I'll just tell you how you always get this. If you take a look at the central moment for a second, you can break it out. Follow me on this, guys. If we wanted the third central moment, consider this all expected value. If we have x minus x bar times x squared minus 2x x bar plus x bar squared, that right there is the expected value of this would be the expected value of the third central moment, right? Just think about this. The expected value of all this, if we use x instead of v, will be 0. So we got that, right? Now multiply this through. You see how you get an x cubed here? Right? That x cubed thing you take to the other side. Now remember, this is 0, but you're going to take that to the other side. And what you have to do is this. You have to get the expected value. I hate to do it all here, but it's going to be x cubed. That's the one we want on the other side. Then we get what? It's going to be, I did all this last night, minus 2x squared x bar squared, or x bar, right? And then it's going to be plus 2x x bar squared. Then it's minus x squared x bar. Minus minus is plus 2. You're going to see this thing falls apart. 2x times x bar squared. This times that is going to be minus x bar cubed. Expected value of all that, right? Follow me? I'm just multiplying it out. I have to do this because it's cubed. Now follow me on this part. Here I got x squared. Here I have x squared, right? Nowhere else. So it's minus 2x squared minus, isn't that right? Did I mess that up? No, that's right. So I can say that this right here will come down to the expected value of x squared, and then I'm going to have minus, and this is going to be 3x squared x bar. And then when I look here, I'm going to have for x, I have 2x here, and I have 2x, so that's going to be 4x squared minus, yeah, this is going to be, let's see, hold on. That goes away. If I counted that, then I'm going to have plus 4x x bar squared, and then minus x bar cubed. I'm sorry I'm taking so long on this. I'm just trying to show you the method, all right? You all with me? I'm just going through the squaring process. If you look at this, this comes to the other side. I'm just going to show you. I'm going to take this to the other side, so it's minus the expected value of x cubed. It should be cubed here, right? That's this power. Get rid of that in here. And now, what I can do is change the signs on all those terms. So this will go plus, this will go plus, this will go minus, and this will go plus. You all with me? And again, just manipulating what was in the expected value class. You all with me on this class? I don't mean to rush on this one. Now, look at this. This is the expected value of x squared times 3x bar. X bar and 3 are constants, right? X squared is what? It's the second moment, right? So you can say this is really equal to 3 times the mean value, and the expected value of x squared would be the mean value squared plus sigma x squared. You all follow me? I'm just replacing the mean. If the expected value of x squared is going to be the mean value squared plus the standard deviation squared. Then it's going to be minus 4, and now look here. This is really going to be, or wait a second. Yeah, this is really going to be the mean value, right? The expected value of x. The x bar is a constant, so is 4, right? So this is going to end up being a mean value. So it's mean value cubed right here. So it's 4 times x bar cubed plus x bar cubed. And you can see one of those cancels, and you end up with this. What I put down there. Here. So let me just put this down. So it's 3 times x. What was the mean value for this problem? I forgot. Is it?
0.5.
Is that right?
5.
5.
Yep.
5, isn't it?
Yes.
3 times 5. So it's going to be 25 here. And what was the standard deviation?
4. Yep.
Standard deviation?
We had a variance of 16.
All right, so sigma squared is going to be 16, right? And then it's going to be minus, and that's 2, times mean value, which is 5, right? Or sorry, not 2. It's going to be minus 3, that's this and this, times the mean value, which is 5, and it's cubed. Pardon me, cubed, my bad. Isn't that what I have down here? Wait a second. I think I messed up the sign on that one. Let me see. Is that right? I mean, can you tell me what that is? I got it. What does he have in his book for this answer?
In his book, his answer is 1750, but he did x cubed equals 3 sigma squared times x bar plus x bar cubed. That's what he ended up with for his like final equation.
I'm over right now. The way you do it is this, though. You gotta expand it out. I'm sorry, I'm cramped here, and I was trying to get it all in here. But that's the way you do it. Remember, the central moments of odd, if it's Gaussian, central moments are 0. If they're even, central moments are just gonna be 1 times 3 times 5 times whatever, times sigma to the nth power, whatever the moment is. Now the reason that's nice is if you want a moment, the central moment, if you expand it, will have the moment in it, and you can take it to the other side. I'm going to give you some homework. The quiz is going to be related to the Gaussian thing that I've showed you today, and the section 5, 2-5.1 through whatever I gave you problems, okay? I just want to get you guys focused on this stuff, and I put everything I'm referencing. That book and the solutions are up there, and you got your old book. I'm trying to just give you stuff that's most useful. Now, here, one big hint here, your calculators do everything else. If you get to know your calculator, you don't have the tape, you don't need the tables, you won't need them. Y'all follow me? And I think, like his, you don't even need to break this down to Q and characteristic or anything. You can punch that right in with the cumulative distribution function. And that's an Inspire. I'm sure you came with a 89, and your HP, I know, does it. Yeah. I'm sorry if I was a little...
You said section 2.5 and then the Gaussian stuff for today?
Yeah, the problems I gave you.